Hi students, welcome to the Sensation and Perception review for the test coming up on either Monday or Tuesday for you. The format of the test will be multiple choice and FRQ just as usual, but I've changed the percentages. So there will be 20 multiple choice questions, but those will only be worth 1 point each. There will actually only be one FRQ. It's got 7 bullet points, and that is actually worth 28 points, which was more like 60% of the overall weight of the test. So you'll get 1 point for defining and then 3 points for applying. So I really want to be able to assess if you know how to apply all of these terms to a pretty big scenario. For those students who are going to be in class, you will have the benefit of using your notes for a little bit of time because I know that people at home have resources at their disposal, so it's only fair that everybody gets to use them. So let's get right into it. If you need to pause, if you need to go back and listen to this again, I do recommend that you write this down. Psychology tells us that when we write it down, we remember it better. So I've posted a clean sheet, if you will, of the review on Haiku as well. So let's talk about selective attention. It's a conscious awareness of a particular stimulus which determines what sensation we will perceive and attend to. The idea in selective attention, and if you remember seeing, the dancing bear when the basketball players are making the passes, we can only attend to so many things. When our attention is deliberately and directly focused somewhere else, we can only go so far. Part of that might be, the cocktail party effect when we hear a name. If you were focusing on those basketball players making those passes, the ones in the white, I think they wanted you to focus on, but somebody said your name, chances are you would have still tried to have been looking for how many passes there were, but you would have been able to tell somebody was talking about you. So it's the ability to detect your name above many voices or stimuli. Sensory adaptation is a gradual desensitivity to a constant stimulus. And what I mean by this is we are gradually, pretty much any stimulus that we're talking about, we're gradually able to adapt to it. So if we're talking a smell, you might notice it at first and then it kind of goes away. If it is a sound, it's really maybe kind of jarring and then eventually you don't really hear it anymore. It's a touch or whatever it might be. So let's get into the eye. Remember, this is a lot about how we both sense and perceive things. So while we mostly talked about the eye and sensation, we very much understand that our eyes have to perceive things as well. So let's just start with the basic structures of the eye. The cornea is the clear, transparent, protective covering of the edge. Of the eye. When you were writing your quizzes, a lot of you said that the cornea processes information or light, which is not really the case. The cornea has a few basic functioning, like for tears and things, but it's really more of a protective covering. It doesn't do a whole lot. The iris is the muscle which regulates the pupil's dilation and constriction. So the iris is a colored part that gets smaller or widens to allow light into your eye. The lens is a structure that changes its shape to accommodate or focus on near or far objects. And when I say accommodate, I'm talking about to either flatten or thicken the lens. When we talked about binocular cues here in class, your eyes had to accommodate. Your eyes had to accommodate to depth perception. At least in most of the classes, we were able to do a little ball throwing. And we know that one eye is probably not as good as two eyes when we're trying to focus on an object that's farther away. The retina is the inner structure of the eye that begins the process of transduction, where receptor cells are detected and concentrated. The retina is the real hard-working part of the eye. It's where all of the neural transmission takes place. The optic nerve is the part of the eye right at the back of the eye near the retina it's the nerve that carries the impulse from the eye to the brain. So the retina sends the message to the optic nerve, and the optic nerve transmits that message to the brain to help us understand what we are seeing. The blind spot is the point near the retina where no receptor cells are located and where the optic nerve leaves the eye. What I tended to say is one day in class when we tried to find your blind spot, I had a couple of volunteers. What one eye doesn't pick up, the other eye tends to do it. But if I'm in the perfect point where there's no receptor cells, because I'm out of your field of vision, I'm in your blind spot. The fovea is the center of the retina where cones are concentrated for fine detail and vision. This is where we have our most accurate, most detailed vision is in the fovea. And remember, the cones are there for our visual acuity, our best vision. Rods are for our black and white vision. We have a lot of rods. Many more rods help us to see at night and in twilight or the shadows when cones don't respond. But it's very important if you think about how human beings must progress and see. Rods are really important. But as humans do get higher on the kind of evolutionary scale, you can understand why color vision is so important. There are fewer receptors, fewer cones, but they are more densely packed in that area of the fovea. Therefore, we have very fine, detailed vision in that part of the retina. The absolute threshold. This is the lowest intensity of a stimulus that can be detected, and usually it's half the time. Now, when I say usually half the time, it's because different stimuli, like one day you might be more attentive or aware of stimuli than you might another time. And so they say like usually half of the time. But at what point can you perceive or sense the smallest bit of stimulus? I want to know, here you do, or here you don't, and then here you do. So it's the lowest intensity of a stimulus that can be detected. This has a lot to do with the signal detection theory. It's our ability to detect the presence of a faint stimulus amid background stimulation. So absolute threshold actually doesn't, or signal detection theory actually doesn't use the absolute threshold. It doesn't have to meet a certain point. Remember, when we talk about threshold, you have to meet that certain point before the neuron will fire. Well, in signal detection theory, it's our ability to detect the presence of a faint stimulus amid other background stimulation. So we're already getting these neural firings, but we need to kind of differentiate. We need to detect one over a different. So intense signals are easy for the brain, but faint signals are difficult. We saw this a little bit when we did the sound localization. When we did the demonstration of sound localization, students were actually almost waiting for the sound to happen because they were trying to sense the movement. Now, they couldn't see or probably hear, but they could still sense, and so they were almost trying to pick up the faint stimulus against other background stimulation. We have something that's called the just noticeable difference, or the JND. I hope you did watch that video that Khan Academy put out. It was a good video to help us understand that there's a minimum amount of stimulus that must be changed in order to produce a noticeable variation. So what's the minimum amount that it has to be changed in order to notice a difference? So when we talked about the threshold, what's the lowest intensity? Well, what's the difference from one in order to notice a difference to the next? That's the just noticeable difference. And it works with this principle called Weber's law. Basically, Weber said the just noticeable difference of a stimulus is a constant proportion or percentage. It's like a ratio. How much more must be added to detect a difference? And you see my little chart over there to the left. What Weber realized, and this was long before psychology even began as a science, is that as the intensity increases, the threshold also increases. And what I mean by that is just what the Khan Academy video said. If you are in a quiet room, speaking in a soft voice, speaking in a soft whisper will be enough to detect the sound. But if I'm in a really loud room and I continue to use a whisper, that whisper is not going to help, because I need to increase, as the intensity of one increases, the threshold of the other. And so it's like a linear effect. It becomes a linear equation of delta and the constant. And so it does use like the absolute threshold. Now, we're not going to get into the 50% of the time, but Weber realized that this is a constant proportion, not a constant amount. Because if you looked at that Khan Academy video, when they were talking about the 2-pound weights or the 5-pound weights, well, if we added 0.2 pounds to a 2-pound, you might notice a difference. If we added 0.2 pounds to a 5-pound, we wouldn't notice a difference. But if we added that same ratio to the 5-pound, perhaps we should actually, hypothetically speaking, Weber's law is pretty good, we should notice a difference. The trichromatic theory. This is the Young-Helmholtz theory, that they realized that the retina contains 3 basic color receptors, red, green, and blue. And they can produce our perception of pretty much any hue or color, which was pretty impressive, if we're talking or 1800s, that they realized that our retinas have 3 color receptors. Working on the trichromatic theory is something called the opponent process theory. Now, this is most useful for explaining color vision and the after images that continue to travel to the visual cortex after the fatigue of photoreceptors. So it has to do with both the sensation and the perception. So the sensation that the stimuli is creating in your retina allows this color to be perceived, or allows this color to be sensed. But when the brain sends it on to when the optic nerve sends it on to the brain for perceiving, it depends on how tired those photoreceptors become. If they're too tired, they can't keep seeing the same color, and so actually the opposite or opposing one shows up. And so it's good for explaining how color vision works. For those of you who were not in class to do the lab that we did, I posted something on Haiku that says, I think it's just called After Images. Take a look at that. They're going to want you to focus on a dot, and then eventually you'll see a little kind of bar sliding across, and the color will change. It's because you've fatigued your receptor cells. Amplitude is to determine the intensity or the loudness or brightness of waves. So we measure intensity, for instance, in brightness, or in, say, decibels for hearing. The gate control theory. This is really kind of we've talked about this a couple of times now. So the gate control theory is how pain is experienced through the spinal cord by blocking signals or opening them to allow sensation to be perceived. So the idea is, if you have a high enough threshold, if the signal is the stimulation, the basic stimuli is being sent from your sensory neurons up your interneurons, it has to be strong enough to kind of open this pathway, to open the gates, if you will, to allow the sensation to be perceived. If it's not a strong enough stimuli, your brain actually doesn't perceive it. It never gets to your brain because it wasn't enough. Now, if it's really, really strong, that gate is going to burst wide open, but then pretty soon something like endorphins. So remember from the last chapter, endorphins will then kind of kick in that chemical response and allow that gate to close, to stop and ease the pain, to ease that intensity. The vestibular sense is the ability to sense body and head position, to understand balance and equilibrium. This has a lot to do with kind of the intersection between our eyes and our ears. And the reason I put it at the end of the sensation is because it's kind of getting us into the perception. So we have to understand up from down, our head from our feet, to understand where we are, to stay upright, to keep kind of an equal balance about us. And this happens deep within our ear in something called the semicircular canals. It's a bit related to kinesthesia, or the kinesthetic sense, which is our ability to sense position and movement of our individual body parts through receptors located in the muscles, joints, and tendons. I think you probably had a good laugh at me when I was trying to do yoga. You have to hold certain movements or postures in yoga, and you really have to focus on individual body parts. But this is pretty much anything that involves movement, even heck, walking. You have to understand where one foot is going. If you've ever twisted your ankle, you realize you lost that flat footing that you needed, or however you were running, or whatever it might have been. And it hurts. It results in a painful sensation. And to do all of this, if you were in class or even if you weren't, I hope you remember the book Zoom. We think of all of these processes of both sensation and perception as either top down or bottom up. Actually, I'm going to start with bottom up processing, because bottom up processing is just that initial stimuli that works on the basic receptors to process toward a higher level. Now, once we get up to through the basic sensation, then we use the contextual information aided by content or expectation to use top-down processing. So there you see the weird shape. I asked you, I'm like, what do you see? What do you see? And we had a whole bunch of things. We had two boxes stacked on top of each other. On the bottom up, we had a lipstick case, we had a refrigerator, we had a window, we had dominoes, we had all these things. But then if we use top down and I put the A and the C on either side, then people are like, oh, I see a B. It's like one of those digital Bs. That's what's called top down. When we have some context, something to make sense of it. I think I also gave you the example of, Chopped, the reality show, where they have to come up with something. They have all these basic ingredients, and then they have to make sense of it. Cake Wars, though, are when you have these incredible works of art, almost feats of science, actually, that are much higher level processing, which is just kind of a basic example. I gave another example of, can you imagine if you had to go to math class every day and learn how to add and subtract again before you learned the lesson? Bottom up, adding and subtracting. Standard deviation, top down, where you're doing much higher level processing. So the ear. We have an outer, middle, and inner ear. It wouldn't hurt to take a look at your book or at that ear diagram to understand how it's divided. Now, you don't need to know specifically, but you do need to know how sound travels through the ear. It starts with the middle. Well, obviously we have the outer ear, but then as we get into the middle ear, we have what's called the ossicles, or these three small bones: the hammer, anvil, and stirrup. The malleus, incus, and stapes. It's in the middle ear, and these small little bones vibrate to transmit the sound waves. So it's kind of like a chain reaction, and each of these little bones start to vibrate the sounds, the waves that are coming down your auditory canal through to your tympanic membrane, and it transmits this sound wave to the cochlea. That's why I have that little arrow there, which is the primary organ for hearing. It's the coil, bony, fluid-filled structure in the inner ear where nerve impulses are triggered. Kind of like the retina in the eye, the cochlea in the ear is where really transduction and all the hard work begins. And this is where the information is then processed and sent on through the auditory nerve to the temporal lobe in the auditory cortex. We can suffer hearing loss if there's some things that have happened to the cochlea. Typically, it's the cochlea. Hearing loss can be from damage, disease, prolonged exposure to loud noises, age, heredity. We have two types of hearing loss. One is conduction hearing loss. That is less common and definitely less serious, and that's when there's damage to those little ossicles, to the three little bones. As small as they are, they can be repaired. What's more common and definitely more serious is sensory neural or neural hearing loss, nerve hearing loss. This is damage to those little receptors in the cochlea. Now remember, in the cochlea, we have those little tiny hairs. And remember, those little tiny hairs are moved around by what's called the basilar membrane. Well, it's that hammer, anvil, and stirrup which actually starts to move those little receptors around. When there is damage to those receptors in the cochlea, that's when we have sensory neural damage. Now, it can also even be things like a tumor growing there or some sort of growth, but typically we see it as like an exposure to loud noise combined with age or heredity. In the ear, we have to understand how we hear different pitch. So there's a couple type of pitch theories that I'd like you to know. The frequency theory is good for low-pitched sounds. It's the rate of impulses matches the frequency of a tone in the whole basilar membrane. Now remember, in the cochlea, we have these little receptor hairs, right? They look like hairs. The basilar membrane is the fluid inside the cochlea. So to understand frequency theory, it helps us to understand low-pitched sounds that is shaking or kind of moving the whole of the basilar membrane inside the cochlea. But that doesn't help us really for high-pitched sounds. Place theory is a better theory to help us understand high-pitched sounds. This is Helmholtz, remember Young and Helmholtz theory. This is Helmholtz's theory that vibrations in the cochlea are triggered at different places. So it's easy to remember places in place theory. So depending on where it happens in the cochlea, whether it's at the base or the apex, determines what kind of frequency or what kind of pitch we hear, whether it's a higher pitched sound or a lower pitched sound. Sound localization. This is when we perceive sound based on which ear collects the wave first. It is difficult to distinguish directly above or directly behind us because the sound tends to hit each of our ears at exactly the same time, and so our brain is crossing that information to the opposite hemisphere, but we can't quite tell which one it hit first. And so it's just that we localize the sound to wherever it's nearest. Perceptual constancy, I have a lot of fun. I'm looking at your Padlets that you posted on perceptual constancy. This is our perceptual understanding of objects despite change. We know it might look different, but it actually hasn't changed. On our retina, it's focusing one thing, or it's kind of perceiving one thing, but in our brain, we realize that it actually hasn't changed. We know things don't like grow and shrink as they get closer or further. We know that if there's a shadow, it doesn't become darker or a different color. We know that it doesn't change even if the angle is different. So we have different types of perceptual constancies. It's like our mind is not playing tricks on us. We see it as our brain perceives it's supposed to be, even though our eyes are telling us it looks a different way. Depth perception is how we perceive objects in 3D, but they're presented on the retina in 2D. So depth perception is good to allow us to judge distance and speed. When we're looking at far off things, it's usually best to use 2 eyes to judge depth. And when we're looking at things closer up, it's actually probably more with 1 eye. When we talk about depth perception, let's talk about visual cliff. There were these 2 guys who basically realized, they hypothesized that babies soon after they have experienced any sort of depth, they will quickly understand it, and basically choose to save their lives. And so if you saw that little baby trying to cross or crawl along that visual cliff, the baby didn't know that they were in no harm or danger because there was a piece of glass or plastic or whatever over there. But because they had already started to perceive depth, because they started crawling, they're not going to cross that cliff because they think they would get hurt. Now, think about when they're 2 months old and they haven't quite experienced as much as they had when they're 8 months old and crawling. They're starting to roll or whatever it might be, 2 or 3 months old, and they have no problem rolling right off the bed. Well, that's because they do not understand that could be dangerous and hurt them. As they get a little older and start to experience, they'll understand it. Binocular cues just basically tell us that 2 eyes are better than 1 to calculate depth and wide scopes. So in the class, we were throwing the balls back and forth, and that was fine. But then when I made you close 1 eye, we realized that that's harder to perceive that depth with just 1 eye. However, there's a lot of instances where monocular cues help us out more actually than 2 eyes, binocular cues. And finally, Gestalt and perceptual set. We will talk about Gestalt again in actually different parts of psychology, but Gestalt in the sensation and perception basically means we integrate information into meaningful wholes. We are looking at the part and we see the whole piece. So we will talk about Gestalt as we talk about, I believe, the personality chapter, but it was when you're able to see the figure and the ground, but you can see it as one continuous piece, but you can also see as one continuous object, but you can also see the pieces of it. And then perceptual set. The context of the stimuli influences our perception. So if we were able to get through that slide, or I hope you take a look at it, there's one that, there's a box in a tree. Well, depending on your culture, depending on your context, depending on your environment, you might be influenced to perceive one thing as, like, say, a tree, but another thing as like a column. When I talked to you about if you were able to see the girl and boy examples, quickly you realized you were looking at your teachers, and then you started trying to decide which of your teachers. You had some context. However, sometimes I gave you real ambiguous ones where you didn't have a lot to go on. So the context of our stimuli influences our perception. That's it. If you have any questions for me, please feel free to email me or send me a Teams chat. I will try to answer as soon as I can. Good luck. Talk to you.